If a valid tableau is available, one iteration of the simplex algorithm is simple. Now the question is, once we have identified the two variables that will be exchanged, the non-basic variable that will enter the basis and the basic variable that will exit the basis, how do we generate a valid tableau for the next iteration? This is the topic of this video. On the left, we have the tableau that is available at the beginning of the iteration of the simplex algorithm. What happens during the algorithm is that the non-basic variable p will be exchanged with the basic variable jq. It means that the tableau that we should obtain for the next iteration should be based on the new matrix B that we call B bar, which is obtained by removing the column A, JQ, and to replace it by the column AP of the constraint matrix. All the other columns are the same. So that's the only modification. And then we need to recalculate all the entries of the matrix. But of course, we would like to avoid an explicit calculation. We would lose the point of the simplex tableau, where the idea is to actually avoid calculating too much. So what we want to do instead is to transform the inverse of B into the inverse of B bar using simple manipulations. And if we are able to do that, we will be able to find easily the new tableau. The simple manipulation that we'll consider are the same as the one that are involved in Gaussian elimination when we solve system of linear equations. They are called elementary row operations. The idea is to consider the row J of a matrix A, multiply it by a scalar beta, and add the results to row I. So row I, that I denote by lowercase a here, index I, the new row I is the old row I plus row J multiplied by beta. It is called an elementary row operation. From a matrix point of view, we see that applying this elementary row operation is equivalent to pre-multiply the matrix A by the matrix Qij beta, and we obtain A bar. And how is Qij beta defined? It's the identity matrix, where we have replaced the element at row I and column J by beta. So what we want to do is to find a matrix Q, which is built by potentially several elementary row operations, such that the matrix B minus 1, pre-multiplied by these elementary row operations, provides the inverse of the new basic matrix. Another way to write this is by multiplying or post-multiplying on the left and on the right by B bar. Then we obtain Q B minus 1 B bar equals the identity. Now this matrix B minus 1 B bar is quite interesting. If you remember, the only difference between B and B bar is one column. Indeed, the matrix B bar has been obtained from B by removing one column and including a new column of the matrix A. Therefore, all the columns of these two matrices are the same except for one of them. It means that the vast majority of the columns of this matrix are actually the columns of the identity matrix. Okay, and we continue like this. And there is one column which contains something else. This is the form of B minus 1 B bar. So it's the identity matrix, except for one column that corresponds to the variable that has been changed. Now, if you look at what we want to do, we would like to find the elementary row operations that transform this matrix here, B minus 1 B bar, into the identity matrix. So it should not be too difficult to do so because it's almost the identity matrix already. What we have to do is to find these row operations that transform only that column, and everything else is already the identity matrix. The application of these elementary row operations is called pivoting. And the pivot is the element which is here on the diagonal of this matrix, UQ. So let's see what kind of elementary row operation can we do using this row, the row of the pivot, as the reference. First, we want to make a 1 here, and we have UQ. Therefore, one elementary row operation would consist in dividing this by UQ, this row by UQ. This is what we are doing here. If we do so, this element will become 1, which is what we need in the identity matrix. Now, each of the other entries must be 0. So let's take one of them. Let's call it UI. What kind of transformation should we do? Well, we need to add something, and this something is the multiplication of the row that we have identified, which is UQ, times the coefficient beta. And what we would like to obtain is a 0 here. So therefore, the beta that we need to calculate will be minus mu I divided by mu q, so that the UQ will simplify and UI minus UI will be exactly equal to 0. So this plays the role of the beta in the elementary row operation. And this is what we have here. For all rows which are not the row of the pivot, the elementary row operation applies this matrix U for row I and column Q, using this value as beta in order to set the corresponding elements to 0. So the result that we obtain after pre-multiplying b minus 1 b bar by this matrix Q is actually the identity matrix. Okay, because each of these entries will simplify to 0, and this one is equal to 1. Now what we have done with pivoting is that we have calculated a matrix Q such that b minus 1 b bar becomes the identity. Now if we move b bar on the other side, we have that Q times b minus 1 is equal to b bar minus 1. And now we can post multiply this by, let's say, the matrix A first, or we can do the same with the vector B. These two quantities here are the one that we need in the new tableau. And these two quantities here are the one that we have found in the previous tableau, the one that we use in the beginning of the iteration. The matrix Q that we have identified using all these elementary row operations in order to change this matrix into the identity is exactly the same one that we need to apply to the tableau. What we have achieved so far is to be able to transform b minus 1a and b minus 1b into b bar minus 1a and b bar minus 1b by pre-multiplying this b minus 1a by q and b minus 1b by the same q. I didn't talk at all about the last row. Actually, it can be shown that the last row can be obtained using the same elementary row operation. In that case, the variable p, which was not in the basis and is now in the basis, we know that the corresponding reduced cost must be equal to 0. Therefore, we apply the same elementary row operation in order to make the corresponding reduced cost equal to 0. Modifying the tableau for the next iteration amounts to perform a series of elementary row operations. This is called pivoting. The column of the pivot is the column corresponding to the non-basic variables associated with a negative reduced cost that will enter the basis. The row of the pivot corresponds to the basic variable that is exiting the basis.